Hi, and welcome back to Book Club. And I know last time might have felt like it was my personal favorite talking through power generation cycles. It is. I just can't ignore these beautiful inventions. Okay, but one, the refrigerator. Right? If you talk about like a change in society, good gracious, the fact that we can keep our milk cold, our beer cold, of course, meats, foods. I mean, refrigeration is truly one of those level up technologies in a civilization, right? And then I live in Texas, and so I will also add on that, air conditioning. That really changes the world of Texas for sure. So, this we're going to talk kind of about both refrigeration, heat pumps, and then I should have time to get into combustion, which is then kind of the next chapter, and just hit the high levels of combustion as well. That's a combustion can get you can go way down a rabbit hole there in combustion. So I'll just hit a little bit of high level and gives you some thoughts. So first up on refrigeration. So I'm going to draw this a TS diagram and show how in the world does a refrigeration system work. So T and then S, and that might have been off screen. T. Okay. So in a TS diagram, and you have some sort of vapor dome. Okay. First off, the vapor dome refrigerants, there are different kinds of vapor domes. Some lean different directions, different characteristics. I'm not going to get into that here. Again, that's another kind of rabbit hole you can get down into. We will talk a little bit about refrigerants. But generically, what I drew here is sort of enough. Okay. And then what's happening in the cycle itself, okay, put 1, 2, like that. And then this is not quite all the way there. All right, but what's happening in a thermodynamic cycle is effectively, you're going to go this direction, okay? And so when you pressurize, and then this temperature is going to be above, let's say this is like a air conditioner. I mean, this is true for a fridge, okay? But this part of the loop of the coil in that refrigeration system is well above whatever your, I'll just say it's external. Okay, so external if it's a fridge, external is your kitchen. Okay, external if this is an air conditioner is the outside. And so even if it's 100 degrees here in Texas, the temperature of this loop, once pressurized up at this temperature, is 120, 140. And so there's room for it sort of to exchange heat with the outside. Okay, and then you drop the pressure usually over. And I'll draw the diagram here, kind of over expansion valve, and then you can reject the heat. Same sort of thing. If this is then refrigeration system. This would be then the internal. Okay, so this is now the inside of my fridge, and what I want to do is sort of run the air over this now really cold portion of the line, and that's where I'll draw it in. Now, a slight shift on this. This is almost starting at the Carnot version, right? Where I put so it's constant temperature, so you can see what's happening. Now, for the same sort of reasons, we don't like to pump. Again, both these situations here. Those are both two-phase systems. You got a vapor and a liquid in there, and that can be pretty rough on pumps and things like that. And so what we usually end up doing, okay, I'll draw the vapor dome again. Well, it was meant to be identical. Okay, what we usually end up doing is starting here and pumping fully in the vapor space. And then you would reject heat all the way until it's a liquid. Okay? And then once it's a liquid, since we're just dropping pressure, usually we just do it across a thermal expansion valve. Okay? And so 1, 2, 3, 4. So 1, 2, 3, 4 from a sort of Carnot point of view, and this is more of your standard cycles. Okay? And so this line here is your pump, and then right, this is your rejection system, so heat out. This is your cooling loop, and then this is just over a cycle. So we'll draw evaporator. So we'll draw sort of a nice diagram here. Okay, through, there's your pump. Okay, so this is state 1 to state 2, and this is Q out. Because again, the temperature outside is going to be way cooler than the line that's through here. And then I'm going to draw it here as well with this little sort of heat exchanger box. And then cross with a thermal expansion valve, and then your evaporator. Evap. And then back up to here. Okay? And so this is then 1, 2, 3, 4, and then, sorry, the same line. 4 is referring to this side, 5 is after the thermal expansion valve, and 6 is after the evaporator. And so what that's going to do here, and I draw this for supercritical CO2. This one above, if you get rid of this section here, this little heat transfer, it's the same thing. Okay. The reason I drew this is actually to talk about CO2, but first let me talk about refrigerants. Okay. And so a little aside here on refrigerants. Okay. And refrigerants are ones that just have good properties here. There's a whole bunch of ones though, like chlorofluorocarbons and hydrochlorofluorocarbons. If you've heard some of that, we got very worried about ozone layer. You know, you got to back up a couple decades, but we're also currently worried about global warming potential. Okay, and so for instance, R22 used to be the name. R22 is just a refrigerant, and you actually see a lot of that now being phased out to, I think it's R410A or 407C or a blend. There's one that was called R12, and that's now being phased out for R134A. Okay, but the reason I drew this cycle down here is actually CO2 does not too bad as a refrigerant. Okay, now what's interesting about CO2, like one of the issues in sort of carbon capture is it's honestly like we have this carbon, this CO2 that it has no value. Now the only value is like stuffing it into soda. So I won't say there's no value, but there's a certain interesting thing that you could do here with supercritical CO2, and the thermodiagram on that one is interesting because your dome here, okay, and actually what's happening, CO2, is that you run it, so this is state 1, state 2, and you're actually bringing it over, there's state 3, and then state 4, it doesn't go down that hard, state 4 kind of comes down over here, and then state 5 crosses it, over thermal expansion valve, and then over to state 6, and then 6 to 1 is sort of reheated right here. Okay, so there's sort of a transfer of Q. What is interesting here, so this is actually considered a supercritical. So anytime your pressure and temperature are above that point, this is a TS diagram, by the way, it's supercritical. And so what's happening is you're sort of, let's go back to the dome. Inside the dome, you come and you hold this constant temperature until you boil, right? And so you start off as a liquid, and then there's this multi-phase sort of, I guess some liquid, some vapor, like a boiling, and then eventually you're fully solid vapor, and then you continue up again, okay? Over here, there's not this big transition. You sort of go from a thing that's vapor-like or gas-like, and then you slowly kind of cross over into this thing that is liquid-like. Now, there's sort of an extended, it's not on this diagram, but it's sort of an extended dotted line that you can kind of say, and like, well, where am I liquid-like and where am I gas-like? It sort of gets this broad area here. If you were to look at densities, it would sort of be around here. But the nice thing is it's a sort of a smooth transition, and so it's easier on systems, and it's just neat from a CO2 point of view. It just happens to happen that this temperature and pressure is not a big deal. For water, you take a lot to actually get up into the supercritical regime. It's kind of crazy. And so supercritical CO2 is super interesting. Okay. Now, there's a lot. I'm actually going to skip past chapter 12. And one of the reasons I'm going to do that is just, honestly, chapter 12 is a lot of that dealing with water. You know, how do you do thermodynamics with air that's humid? Psychrometric, I think is the term. I'm screwing it up. Again, it's sort of I won't say it's a niche industry, but certainly you can go through there and do the applications. You're just having to now, where most of these cycles we're not tracking sort of the constituents. We're all saying it's, like in this one, this is all CO2. Or even in the Brayton cycle, we're saying it's all air. We're not tracking the different constituents. If you have air and water, you actually can track those. And there's some pretty interesting things. Like we had a family lake house out in West Texas. And when it's super, super dry, actually all you need to do is sort of blow air over some straw that's wet. And by just adding the humidity, it actually pulls down the temperature of the air. And so there are things like that. Those are called swamp coolers. So if you're interested in that, you can hit it up in chapter 12. So I'm not gonna dig into it. But what I'm gonna finish off on this sort of section now is actually into combustion. Okay. And one of the reasons I'm going to do that in combustion is just the kind of the basics of it. Okay. So this is now kind of chapter 13, if you will. And this is getting close to almost being done with the thermo, and then we're going to come back into the fluid mechanics and add some more richness. One of the simplest combustion equation is actually the combustion of hydrogen. Okay, it's pretty flammable. And if you had a chemistry class, you know this is H2O, and so you actually go back and balance that and say, well, I need 2 moles of hydrogen to get that to sort of balance out. Okay, and then you know usually though you don't, at least in the combustion physics world and rockets and aircraft, we don't talk about moles. We usually talk about it might be an O to F ratio, and that's referring to the mass of oxygen to the mass of fuel. Okay, and so here you say the mass of the oxygen will have 2 molecules, and then the molecular mass is 16, kilograms per kilomole, and you're welcome to use grams per mole or whatever you're doing. And then here I have then 4 times 1, 2 here times 2 here, and the molar mass of hydrogen, kilograms per kilomole. Okay, and so you end up seeing that this is 8, and that would be perfectly balanced. So there's no extra terms here. This is called stoichiometric. Okay, and usually you would refer to this in terms of O to F. Sometimes you might hear is stoichiometric. So if you have more fuel, so if this became a 3, okay, let's say this became a 3, then that would be a fuel-rich system, and so the O to F would actually go down. And then if this was a 1, that would be a lean system. Now, if you get into combustion, especially in cars or even aircraft, there are certain times where you want to be running lean, certain times you want to be running rich. It depends a lot on the inner workings of the system, temperatures and things like that, and burn. Okay. You can also, now let's go a little bit more complicated. Let's say it's methane, CH4, and you can actually, if you wanted to account with a nitrogen, sometimes you just do this trick where you just add 3.76 nitrogen, and you would leave out here as the balance. Okay. If you do that, you actually balance it out to 6 CO2 and, well, not 6. This is meant to be A, B, C times O2, and then you got some nitrogen. Okay. And the book talks through, like, if you want, you can write system equations and solve this. And so you can go ahead and do that. And then usually since it's talking about air, use the air to fuel ratio here. If you go and then do the math, this is 17.19. Okay. And then the 2 final pieces to sort of talk about here at the high level, and then I'm going to give you sort of the couple-minute deep version of combustion physics. Okay, 1, you can kind of solve for a lot of this, but 2 is the heating value. Right? And now you have a lower heating value and a higher heating value. And the lower heating value is where you sort of include all the water goes to vapor, and the top one you don't. So you got to be careful. Depending what calculations you're trying to do, you should be using the higher heating value, the lower heating value. So just be careful on that. It does change, it makes a difference. Okay, combustion. So this is sort of the highest level of combustion physics. If you're actually talking about engineering behind combustion, it gets really crazy. So the first thing that you would say is this is sort of the highest level equation, but actually the chemical kinetics, when you get down into it, like I remember being at a conference and someone was saying, yeah, I had a 3-step model for my combustion simulation and my CFT simulation. Like, well, maybe that's okay. But then the next person over was like, oh, I'm using 10. And the next person over here was saying that they're at 100. And then the last person piped in and said, guys, let's be clear, we all know it's 2000. You know, they were talking about. So it's 2000 separate equations for all of this, as sort of the chemicals are coming off and there's equilibrium, and then this one fires here, and then this. So the actual root of chemical reactions can be quite crazy. And really, from an engineering perspective, when you're building these systems, a lot of what you are having to solve for, okay, is the kinetics. So how fast is it going to happen? Okay, like if I'm a gas turbine, I actually need to light it and know, like, if it's a really slow kinetic, then my combustion chamber is going to have to be long in order for that to light. So kinetics are a big deal. I know right now in global warming, we're worried a lot about the CO2, but it doesn't take too far back to rewind. What we were actually worried about for a little while was the NOx. And so, this sort of pesky N, if it's not stoichiometric, you could actually end up having a whole bunch of NOx that shows up, okay? And then I'll just sort of find the final point is each one of these reactions, like that's happening at a molecular level. And so within a combustor system, right, the variations around, like this pocket here actually might be fuel rich, this pocket over here might be fuel lean. There are strategies where you actually might want to burn rich and then quench lean. That happens a lot for different reasons, but all of this can actually vary within systems. In fact, in rocket propulsion, and I'll get into this in the next book club, but usually what happens, if I plot sort of O to F versus ISP, there might be this magical point here where if I could just nail this point, I have the highest O to F. The problem is within my combustor, I'm not nailing it. I'm actually bouncing back and forth. Like here, in this part of the rocket engine, I'm over here, and this part of the rocket engine, I'm over here, because I'm not perfectly mixed, right? And so, in fact, one of the ways you improve your rocket engine performance is by, if you can get it to perfectly mixed, then you're actually tightening up this band, and your ISP goes up. Okay, so combustion is actually quite it's quite a science all into itself. Ignition, like getting things to light, is quite a science into itself. Emissions is a whole other process, and even if you're thinking about gas turbine engines and like qualifying them for aviation or flight like that, then emissions and what you have to do to track is quite a bit different. And then if you look at like car engines that are built for racing, where they don't necessarily have some of these emission criteria, it's going to be a very different car engine than one that you have to handle all these emissions. So there's a lot there in the world of combustion. And so that's kind of a high level. Go read this chapter, of course, but in the thermodynamics, it's really just sort of high level, because we sort of talk about heat addition almost all throughout thermodynamics. So it sort of makes sense to do at least a little section on, like, well, how are we really adding heat? And it's this chemical reaction. We don't usually talk about nuclear reactors a ton. There might have been a few examples inside of the thermodynamics book with nuclear reactors, but a lot of times we're just kind of talking about it in the perspective of combustion. Okay, so that was refrigeration and air conditioning systems. A little touch on combustion, and then honestly, like we're kind of done with this. So if you go and look at chapter 14 in this book, is actually the start of statistical mechanics. Well, I already did that earlier in the lecture series, getting into statistical mechanics. I find that to be a more useful start. Maybe it's a little bit more math heavy. I find that to be more useful to start then. So entropy hopefully means something more, as opposed to sort of this late addition, late using entropy definitions in statistical mechanics, right? And then a little bit of that kind of equilibrium. So we're going to move on to And the next one is kind of back into fluid mechanics. So we'll see you next time on Book Club. Remember, if you are enjoying this, like and subscribe, and we'll see you next time.